Welcome to Atoms and Elements, part 1B. So this will be a continuation of our study of the structure of the atom, and here we're going to look more closely at what's going on with the electrons. Let's get started. All right, so we remember that matter is anything with mass and volume, and we want to connect that with what we know about the structure of atoms. So we know within the atom that it's the protons and the neutrons that create the mass and the electrons that create the volume. And of course, the protons and the neutrons are localized in the nucleus. All right, so we've already covered that pretty well. Let's look a little more closely at the electrons. So what else do we know about the electrons other than they create the volume of atoms and therefore the volume of matter, right? Well, we know they have a negative charge, and we know that that negative charge, right, is attracted to the nucleus. And of course, the reason for that is because the nucleus has the positively charged protons. We also know that electrons don't like each other. They find each other quite repulsive, right? Electron repulsion, right? How much do electrons hate each other? They hate each other so much that they can prevent a supernova from collapsing and forming, right? Eventually, gravity takes over. But electrons do not like each other, right? And what else do we know about them? They are constantly moving. All right, so let's see how all of this comes together into the structure, the structural aspects of electrons within an atom. All right, so we can think about the electronic structure as a peace agreement, right, between the electrons, which don't like each other and want to stay as far apart as possible, right, with the electrons being attracted to the protons. All right, so we have to come up with a balance inside the structure of the atom. All right, so what happens is the electrons travel in these mathematically defined regions. So if you want to get into calculus, you can go into the Schrodinger wave equation and all kinds of trippy stuff. But for our class, we don't have to worry about that. We can stay at a very simple level. Basically, the electrons are traveling in regions called shells. And they're three-dimensional in shape, right? These can be divided into subshells and orbitals. But the great thing about our class is we can focus right here on the shells. That's enough for us. All right? So when we're describing the shells, and these will be the larger regions, the larger groupings, and that will be fine, okay? So we describe the shells using the letter N, right? So N is any integer, 1, 2, 3, can go as big as we want. Of course, we run out of atoms. The shells with the higher value of N, the larger value of N, have the higher energy, and the shell will be larger, and it'll be further from the nucleus. So let's look at an example of that, right? So here we have hydrogen, right, with its one proton, and it has no neutrons, right? So remember down here, that's Z equals 1, the number of protons. That's called, you should know it, atomic number. And then up here, we have the mass number. You should know that too. We only have one proton, and so there's no neutrons to add. Now, how many electrons would we have? Well, this is a neutral atom, so if it has one proton, it's going to have one electron, and that electron is symbolized right there in the first shell, right? So we would symbolize this as the N equals 1 shell, our first shell. Okay, and then as we go on to helium, it's a slightly larger atom, right? It has 2 protons, and it has a much larger mass number. So now we see once again, right, if there's 2 protons, we're going to have 2 electrons, And those are symbolized here. Once again, they're still occupying the first shell. Now, when we get to lithium, though, we have a larger atom, and this isotope of lithium would have 3 neutrons with the 3 protons. All right, so now we see once again, this time we have 3 electrons. So notice that the first 2 electrons go into the first shell, but now this shell is full. And so the third electron has to go into the second shell, right? And we see as the shell number gets larger, right, the shell gets bigger. All right, so as we would suspect, as the shell number gets larger, as the shell number is higher and the shell gets larger, we can hold more and more electrons. So the algorithm here is simply 2n squared. So if we're in the first shell, as we saw on the previous page, 2 times 1 squared would be 2 electrons. And when we saw with lithium, the first 2 electrons go into the first shell, but now it's full. That's why the next electron had to go into the second shell. So the second shell can hold 2 times 2 squared, or 8 electrons. And the third shell can hold 18, and the fourth shell can hold 32, and you get the pattern. We could keep going. Now, the important thing to know about electrons is they are not all equal. The outermost electrons are called the valence electrons. And these are going to be the important electrons for us. This is where chemistry happens. The core electrons, they're basically held trapped next to the nucleus. All right. So let's make some notes here, right? So valence electrons, right? They can be gained or lost, right? We could add some more in, or we could lose some, right? By atoms. All right. So when we gain or lose, that's going to be ionic compounds. Or those valence electrons can be shared to form bonds. We'll put covalent there. Okay, and we'll talk more about this down the road. The first thing we have to do is understand what's going on with the electrons, and then we can learn more about how they're gained, lost, or shared. Okay, on the flip side though, the core electrons, they are basically held tightly by the nucleus. So they're not going anywhere, right? We can think of them as being trapped. Alrighty, so let's take a break here and look at how this all fits together and introduce one more concept, the concept of core charge. Alright, so let's look at lithium. How many electrons are in the valence shell? Right? Well, the valence shell is the outermost shell. So if we look at the outermost shell, n equals 2, we see that there is only 1 electron. Then how many are core electrons, right? Everything else is core, all right? So we see there we have 2 more electrons, and that accounts for the 3 electrons of lithium. Okay, so now we can get this idea of core charge, right? So the core charge would be the charge right here. So it's the nuclear charge and the core electrons. Okay, so the nuclear charge, right? Lithium has 3 protons, so that would be plus 3. Now we're going to add to that the core electron charge. Well, there were 2 core electrons, so our core electron charge is minus 2, so we get a plus 1. So the core charge of lithium is plus 1, right? Nuclear charge, which will be a positive value, and core charge, which is a negative value. All right, so the core charge will always be positive. Okay, so now let's, core electrons, that's about it. The only thing we really need to know about core electrons is we want to know about core charge. Really, valence electrons are the big deal, so let's look more closely there. Alrighty. So the cool thing is that the periodic table is arranged so that the elements with the same number of valence electrons occur in the same column. So these columns are called groups, all right? And then we can look at the group number at the top of each column to figure out the number of valence electrons, right? So the number of valence electrons is the group number. Now, old school, it was just these Roman numerals, so it was really simple, right? So if we look there, if we look like group 2A, right, Roman numeral 2, right, or we see the 2 on top, right? Either way, we know that this column has 2 valence electrons. Over here on this side, recently we added the more Arabic with the 1-6. So then you would focus on the 16, the 6, or the Roman numeral 6. Either way, we know that this column has 6 valence electrons. So as we read across the table, right, so group 1 is going to have 1 valence electron. Group 2 has 2. Now we're going to skip the transition metals. Group 3 has 3 valence electrons. 4, 5, 6, 7. And then the noble gases, this is where we have the 8 electrons, or the octet. And we will see, just like with the noble gases, that that is very stable. All right? So basically all of the elements, they're going to gain or lose valence electrons to try to be like a noble gas, to try to be stable. All right? So remember, right, that the number of core electrons is simply the total number of electrons minus the valence electrons, right? So we always know the total number of electrons because the number of electrons equals the number of protons. And then the valence electrons we get from the group number. So we can always find this information from the periodic table. And then simply the core charge, didn't quite leave it, right, is the nuclear charge plus the core electron charge. Okay, so let's practice these important concepts a little bit right here. So if we look at like oxygen, right, we just did this one as a practice, right? Now the total number of electrons, oops, that was a boo-boo, right? That should be an 8, right? If we look, there's an 8, there's 8 protons, so there would be 8 electrons. The number of valence electrons is 6 because it's a group 6. So the number of core electrons is all the electrons left over. So 8 minus 6 would be 2. So what's the nuclear charge? Right? We would have 8 protons and we would have 6 core electrons. So, oh, I'm sorry, I jumped ahead. That should have been there. Right? The nuclear charge is plus 8 because we have 8 protons. And then the core charge is those 8 protons and those 6 core electrons. So that would be, yeah, so the core charge would be plus 2, right? Because we had the plus 6 there, and then the 6 core electrons. Alrighty, let's do another one. Let's see. Aluminum, right? Aluminum has 13, right? 13 protons, so it has 13 electrons. Where is aluminum? Aluminum's in group 3. It has 3 valence electrons, right? So the total minus the valence gives us the core. All right, the nuclear charge is very simple. It's the number of protons. So the core charge is the nuclear charge, right? And then the number of core electrons. So that would be plus 3. Oh dear. I see that I'm sorry, I have to go back. I see that I messed up oxygen. Let's start over, right? So the core charge should be the plus 8 for the nucleus, and then the number of core electrons would be minus 2, right? So for oxygen, the core charge is plus 6. Voila. All right, I'm glad I found that mistake. Okay, and then potassium, 19 protons, so 19 electrons. Potassium, we look right here, group 1, only 1 valence electron. That means all the other electrons are core. The nuclear charge is 19. So the core charge, we have 19 protons, and we have 18 core electrons, which gives us a plus 1. So maybe I'll circle those in red so that we can distinguish them. There we go. So there's all of our core charges. Alrighty. Now, let's look at one last topic to finish up this video. Valence electrons are important to chemical reactivity. So, the chemical properties are determined for an element by the number of valence electrons it has. Elements can gain or lose their valence electrons, right? That would be for ionic compounds. Or they can share electrons, and we'll see that will be covalent compounds. So, right now we're going to focus on ionic compounds, and we're going to look at metals and nonmetals. Now, to distinguish between metals and nonmetals, notice that there is this stair-step line. So, the metals are to the left, and the nonmetals are to the right. All right, so metals, they are going to lose electrons. Okay, and depending on how many they have, right? So like lithium has 1, so it's going to lose 1. Magnesium has 2, it's going to lose 2. Aluminum has 3, it's going to lose 3. That's why we put an X here. It depends on the metal, but all metals are the same, that they like to lose electrons. So here are those lost electrons. I think that would make a good movie title. All right, now the nonmetals, on the other hand, we'll just kind of symbolize that nonmetal, all right? They are going to gain electrons. And so by gaining electrons, they will gain a negative charge. All right? So the number of electrons lost or gained is always going to correlate with the valence electrons to get to an octet. Now, let's look a little more closely at the metals that like to be positive and the nonmetals that like to be negative. Alrighty. We know metals are good conductors. And nonmetals are poor conductors. Right? So that means they're good insulators. Alrighty. Now in the middle, we have some elements that take on the qualities of metals and nonmetals. These elements that I've marked in green, these are the metalloids. And they're also called semiconductors. Right? So those of us that enjoy computers and cell phones and any kind of gadgetry, semiconductors are part of that pleasure. Okay, So now let's just do a couple questions to wrap up. What is the charge of the ion formed when the following atoms lose their valence electrons? Calcium. We find calcium right here. We see it's in group 2. So we know it has 2 valence electrons, right? So it's going to lose 2 electrons. So that's going to give us a +2 for calcium. And then aluminum. Here's aluminum, right? It's group 3 or group 13. There we go. So it's going to lose 3 electrons to be aluminum 3+. So we know they're going to lose electrons because they're metals. We also know it takes energy to gain or lose electrons. So it's much easier to lose 2 than gain 6. Or lose 3 and gain 5. Non-metals, on the other hand, right, to the right of the stair step, they're going to gain valence electrons. So if we look back at our buddy oxygen, right, it's going to be group 16 or group 6, right? So if we have 6 + 2, we got to get to 8, right? So oxygen has to gain 2 electrons. So it's going to make the oxide ion. And then our buddy, there's oxygen, and then bromine's right here. Bromine is group 7 or 17. There's the 7, right? So 1. So bromine needs to gain 1 electron to achieve an octet. Alrighty, so that wraps up our overview of the electronic structure of atoms. This would be a great time to work through a few practice problems to reinforce your understanding.